this is the beginning of our, this is outlining the process. So we had this three-step process. The laser field is applied, and the intensity is set such that the electric field is less than the binding energy. If it was equal to the binding energy or more, you'd have an outpouring of many electrons, and you'd have a plasma, and you would not get this return of accelerated electrons. You would not get high harmonics. You would get a laser-produced plasma. So the intensity is set so that the electric field is much less than the binding field, and then the way an electron gets out is by tunneling. Okay, so the electron tunnels out, and the three-step model assumes that after tunneling out, it is then a free electron in this same laser electric field, born with, at time zero, with energy zero. Okay, no kinetic energy. So the model is that the tunneling just gets it out of the atom. It's then in the laser field. It accelerates away from the atom, the ion, and it comes back. And depending on when it was born in the phase of the electric field, depending on when it was born, it will return with varying kinetic energies, or maybe never return. So for instance, if it's born right at the peak of the pulse, either positive or negative, the electron goes away, it gains a lot of energy, kinetic energy, but it returns, because the electric field reverses, it actually returns with no kinetic energy. So being born at the peak of the pulse, not a good idea, doesn't work so well. It can be born at any other time in the pulse, but some of the important cases were one born at the peak. Another important case is born at 18 degrees or 198 degrees, et cetera, et cetera. So 18 degrees after any of the peaks, which is roughly pi over 10. That is the case where the return energy is a maximum, okay? And by the way, in that case, if there is a recollision, recombination, radiative recombination, the photon will leave, has the potential to leave with an energy equal to the return kinetic energy plus the original binding energy, okay? So it'll have both of those, okay? And there'll be a pulse of photons with that high kinetic energy at each of these points. But that's not to say that there isn't emission also for electrons that were born at these other times. They will also go through this multiple times per pulse, but they just won't have the same, their kinetic and their emitted photon energies won't be quite as high. So there'll be some spread of photon energies. And then the last case is if the electron is born, let's say just before the pulse, before the peak of the pulse, or in this region here, it actually never returns, okay? In the case of where the electron does return and there is recombination, there's a probability of recombination, but it's not a sure bet. In fact, the likelihood of the recombination and emission of a photon is small. It's like 1 part in 10 to the 4th, or at higher photon energies, maybe even 1 part in 10 to the 6th or less. One of the reasons is because the electron is going a few nanometers away and coming back, and there's a sort of an electron, quantum diffusion is what they call it, but the electron is a wave function, has an associated wavelength, wave function, and it's emerging from a very small spot at a finite wavelength, and so there's an angular spread as the electron leaves, okay, and it's spreading in angle, and so when it comes back, it's spread over a much larger area, and that accounts for something like 10 to the minus 4 in itself. I'm sorry, accounts for something like maybe 10 to the minus 3 or something like that. Okay, so I wanted to go back to this slide. So most of the cases, many cases that people look like are for neon, where the, depending on the pulse duration, the laser pulse duration, let's say for 10 femtoseconds, you would pick a peak laser intensity of let's say you're up here, something like 5 times 10 to the 14th or 6 times 10 to the 14th watts per centimeter squared will get you the electric field that you want. Okay, but if you wanted to get to higher photon energies, you might use helium, which has a higher binding energy. So on recombination, the emitted photon could have that same high energy, actually even more, because now it's at a higher intensity, therefore a higher electric field. So it's going to return with a higher kinetic energy, and it's going to have a higher binding energy. So this would be a way to get higher photon energies. And why does it take higher intensity? Because of the higher binding energy, there's less shielding of those valence electrons. Here and at the argon and krypton, there's more shielding of the electrons, so the nucleus is shielded more. So here with helium, not so much shielding. You need a higher electric field to get the tunneling to go. Okay.
Professor Attwood?
Yeah.
For the ionized fraction here, is that fraction of all electrons within the atom, or
No,
is it just per atoms in the gas?
Yeah, it's a number of atoms. So it's saying that what we want is we want the tunneling to be only 1 electron per atom. But this would say that in this case here, this is a 10% ionization, meaning 10% of the neon atoms actually yield an electron. Okay, and you don't want to go any higher than that, because if you go higher, you start to get too much ionization, too many free electrons, and it affects, as we'll see later, it affects. So good question. This is the fraction of atoms that are going to ionize.
Professor,
okay.
Yeah.
How much overlap is there between like the first ionization probability and the second ionization? Is there a lot of overlap there, or is it pretty discrete and we're able to like separate those two events?
You know, I could look it up real quick, but the answer is I don't know. I think these are valence electrons, so they're not going to be a big difference, right? In ionization potential, it's not going to go up that much. It's not like you were at the K shell or L shells where there's a really big difference. So, but the electric field compared to the binding field is quite small. It's less than 10%. So I think my understanding is we're just going to get 1 electron per atom, but it's a good question and I don't quite know the answer. Okay.
Professor?
Yeah.
This may be kind of the same question, but yeah, I'm just like surprised to not see the ionization fraction ever get above 1, because I would think with like a super high intensity, you'd end up pulling off too many, like multiple electrons per atom.
You are right about here. Let me see. I don't remember. Whoop, maybe that was it. These are ionization. Can we read it? What does it say? Approximate number of ions produced versus intensity, and you can see that some of these things are getting up high. I think. Here, yeah, this is what I was looking for. So here's this is sort of pre-high harmonic studies, just pre-1992. And you could see that for different laser intensities, they were producing neon plus 2, plus 3. So this sort of relates to your question, I think, right? And you're seeing that with high enough intensity, you can start pulling off more electrons. Yeah, so for instance, what would we say here? At a laser intensity of 10 to the 15th, you would get an order of magnitude more single ionized than double ionized. So maybe that also relates to Josh's question, okay? So it depends on where you are, but there's sort of an order of magnitude. If you're down here someplace, if you're down, let's say this is showing us that below 10 to the 15th, this is neon, I think also, right? yeah, I think it's neon. But at any rate, if you were down here below 10 to the 15th, there's basically no second ionizations, whereas you're getting very high number of ionizations with single ions. Okay, so I guess we did okay on that. So then we went to the equations of motion. You know, the Lorentz force, E plus V cross B, mass times acceleration. We solve for the acceleration, integrate twice, and we get a velocity and a position, and we have some constants of integration. But x0 is the place of birth, and we call that 0. That is 0. And we also say in this three-step model that the initial velocity, just as it comes, just at the time of birth, sort of, as it's just been liberated through the tunneling process, V0 is also, we'll solve for V0 in a second. No, I'm sorry, V0 at time T0 is 0. So these initial conditions go out, and now we can solve for the velocity as a function of when the electron was born, okay? And what is the position? And if we solve those equations, these are the equations that we get. And by the way, there's a comment here about you have to correct it, make a correction in your book. And also you should all look at the errata, because there's a bunch of little typos. Some of them are really obvious, none of them are really important, but at any rate, there's a lot of them. Anyway, you're just solving it, this classical motion, and you have that the velocity as a function of time depends on where you are in phase and when was the electron born, this phi0. So this is the one that's variable. If this is 0, this thing comes back with no energy. If this is 18 degrees, that's when you get the maximum. But lots of things are possible. And this is the solution, one more integration for the position. And this, you have to solve this numerically. Okay. Oh, I don't think we want to go through all of this, but this was an example. This was, I think, neon again at 5 times 10 to the 14th. So, and this is then the position. And you notice in this example, it's 2 nanometers with these functions, with these phase functions. Depending on the phase function, this part can give you another factor of 2, and you could get an excursion of 4 nanometers. And for instance, born at the peak of the pulse, that will give you 4 nanometers excursion. That's time to gain a lot of energy, but it comes back with nothing. And this is the electron energies. And again, you have to solve them. But for instance, in this example, the return binding energy would be 60 eV, but it depends again on the time of birth and the time at which it recombines, okay? And by the way, this would be 60 eV, but if it's in neon, there's another, it says right here, 21 eV. Another 21 eV was the binding energy to pull off that electron. So it would be a total of 116 eV, okay? So then we go to these curves, and so these are numerical solutions, but so here's how to read them. Again, this is neon, 5 10 to the 14th, 800 nanometers. And these are different times of birth. Every one of these blue curves is a different time of birth. You can't resolve them here, but in this phase is in the electric field. So here is the electric field. So this is the 0 phase set, and here is 1 cycle, okay? And for instance, this lowest curve, this is the one that was born at time 0, okay? This is when the electron, so the electron goes and it goes through a distance from the ion of 4 nanometers. That's what's happening here. And then it comes back and crossing the axis, this is when recombination occurs, and it has no kinetic energy, okay? The one that's most interesting is so there are all of these other different times of birth, but this one that comes at pi over 10, which is kind of hard to read here. It follows this path, and what matters is right here. This is the recombination time. The rest of this only matters if it misses the ion. So we're interested really in what's happening right here, okay? And this is the kinetic energy, the return kinetic energy for these different paths, depending on what the birth time was. And it only doesn't even go to pi/2. It's just in this region for birth times, okay? So what's interesting then is, so this is the peak, but there are these other birth times that are also producing energy, okay? And the next slide shows us, oh, I'm sorry, and here are the, it's just a labeling of when they were born. In this case, we're thinking, okay, we've eliminated a lot of the curves. How did we do that? Well, we put a multi-layer mirror there that had a bandpass of just 5 degrees. So these are the different birth times from 8 degrees to 28 degrees. And this is the total, this is the kinetic energy of return. And this is the total energy of, with the binding energy added in. So for instance, if you look here, this is 116 eV. So if you took, did I do this right? Yeah. So what is the percentage energy here just between these curves, between the 13 and the 23, you're going from 111 to 116 to 112. So this group of 3 is all we're looking at here. So we've chosen a filter, or more likely a multi-layer mirror, that just allows 5% total bandwidth. All of this is within 5%. So we could do that with a multi-layer, or some multi-layer and a combination of a filter perhaps. And within that, these would be, we would only see the purple and 1 blue to each side. And if we follow them back, their time of recombination, when they cross the 0 distance from the ion, this is recombination time for all of them. And the variation is only 200 attoseconds. So we are into, if we use a bandpass here, we're into 200 attosecond pulses. So any comment, especially from any comment from anybody, but from the people who are knowledgeable about high harmonics, does everything seem to be hanging together okay? Okay. This is just showing, okay, so there's emission in this region or beyond the peak of the pulse to around here someplace. That's when this is when the successful electrons were born, but there's a time for them to go and come back, and that's what this dashed line is showing for some particular harmonic. And then there's the burst of energy on recombination, and it's periodic. And because they're also perfectly separated in time, so symmetrically, then you get these spikes. And if you see this flood of photons coming, different photon energies, let's say from different, will be there at the same time, and you can filter out what you want. But basically, this is only going to produce odd harmonics. So if you did a Fourier analysis of a pulse structure like this that was coming out, you would only need odd harmonics. You would only need even harmonics if there was something else in the middle here and it wasn't centered properly, okay? And people do that on purpose. They use, they drive with 800 nanometers and 400 nanometers at the same time, and it breaks the symmetry. And rather than get this perfectly separated peaks, there's also something else in the middle, breaks the symmetry, and you can get even harmonics in that case. Recombination, radiative recombination with the parent ion. So we don't need to read this so much unless you want. But what I wanted to show you was this graph. So this is a collection of experimental results. It was originally done by this, I forget his name, Michael Schnurrer. he put it together, just reviewing all literature. But it's in some review papers by he and Krauss and other people. So this is the harmonic conversion efficiency, which is dependent a lot on that recombination. And this is showing that for different harmonic orders. So in the extreme ultraviolet, which would be in here someplace, for instance, a harmonic order of 100, so you have this would be 8 nanometers in wavelength. So that's pretty short. And this is the carbon edge over here. So most people typically work in this region, okay? And so let's say 40, I know we only have odd harmonics, but just to make the numbers easier, 800 nanometers by 40, so this seems like it would be 20 nanometers here, okay? And this is showing the yield being higher for argon, less so for neon, helium starting to fall off. So here you're getting to higher photon energies, but the conversion efficiency is dropping. You see here it's down to 10 to the minus 8. So people are pushing to get into higher photon energies because they would like to have attosecond, 100 attosecond or less pulses with higher photon energies to probe more kinds of materials and more energy levels. But one way of trying to do that is using not 800 nanometers, but a longer wavelength, like 2.4 nanometers or something. And if you remember the formula, it's back in one of the very first slides. The photon energy that you get is you recapture the binding energy, and then it's something I lambda squared, intensity lambda squared. So going to longer wavelengths allows you to get, by lambda squared, allows you to get higher photon energy. So rather than be, let's say, at 800 nanometers, if you went to 2.4 microns, that's a factor of 3, squared is 9. So you can get much higher photon energies, and rather than say 30 eV, 300 EV, get around the carbon edge. The problem is that the excursion distance that we were just looking at before also depends on wavelength squared. And so the excursion distance is increasing, and therefore the likelihood of recombination is dropping, and that's what we're seeing here. But basically that is what everybody sees. You can get to higher photon energies, but you're going to have a much lower conversion efficiency. And by the way, this is into a single harmonic, I think. Any comments? Or
I have a question about the x axis on this plot. It says harmonic order. Is this the harmonic? And I'm kind of confused as to what it's referencing.
Yeah, no, very, very good. This, for instance, in the equations, I used H. So if we started with 800 nanometers, and again, let me use an even number just because the division is better. For instance, for 40, harmonic order 40, that would be H equals 40. That's be 800 over 40, so that'd be 20 nanometers right here. And this would be 8 nanometers, okay? So we won't have even harmonics, but we'll have odd harmonics sort of just over here. So we might do 800 nanometers divided by 39. And that would give us what wavelength we're going to see. So harmonic order means it's the multiple of 800. It's 800 nanometers divided by this number, which we have been using the letter lowercase h for harmonic. Okay, to answer the question? That's okay?
Yeah, I think so. Yeah.
Yeah. So for instance, sometimes when we do frequency conversion with a laser and a crystal, we'll say we're going to the second or third harmonic. So that would mean that if we were starting with 800 nanometers, the second harmonic, so-called n equals 8, in this case we'd say h equals 2, but n equals 2, 800 nanometers divided by 2 is 400 nanometers. And 800 divided by 3, which is something you can also do with crystals, is just the 800 divided by 3, whatever that came out to be, okay? So that's a harmonic order or harmonic number. And I just copied this. This is the way I think people use both harmonic number and harmonic order. Here's that equation, by the way. The maximum photon energy you can get is the ionization potential. You're regaining that on recombining, plus this is the formula, lambda squared. I lambda squared, the intensity, which would be like the 310 to the 14th, times lambda squared, 800 nanometers or 2.4. And this number just comes out of those numerical solutions of those equations where we saw that there was a peak energy, okay? And in the early days when they had the three-step model, they would just put a 3 here or a 3.2 later. And it was only later when they started solving the equations that they found where this number came from. Okay. So we talked, it's high spatial coherence. The incident laser, if it's a Ti sapphire, is spatially and temporally coherent to some degree. And that's being impressed on this whole process. And so the harmonics are also spatially coherent. And this is a measure of that using Young's double slit. For the spectral part, what do I want to say here? I would say there's two parts to this. We would normally have said that, oh, the bandwidth is 1 over n. If there are n cycles, it's the spectral bandwidth is, you can expect to be something like 1 over n. There's going to be some engineering details to that, but some technical details. But basically, if you're 800, let's say that your Ti sapphire pulse is coming in, and it has a bandwidth of 10 cycles, and you're looking at the 25th harmonic. Okay, what that means is that for every cycle in the infrared, there are 25 cycles in the harmonic. So you would think that your bandwidth is going to be not just the 1/10 for the infrared, the Ti sapphire, but also multiplied by 1 over 25, because there are going to be 25 harmonic cycles for every infrared cycle. Okay, so if you have an infrared cycle, if you have an infrared pulse that's 10 cycles, and you're looking at the 29th harmonic, then I would expect you're going to see a bandwidth of something like 1 over 290. Okay, and this graph was just to show that it doesn't much matter if it's a rectangular wave packet or a Gaussian wave packet. They both give almost the same relative spectral bandwidth, so that's not a big factor. Okay, but my simple theory doesn't always work. So this is some real data from Thomas Pfeiffer, who I think he was here in Steve Leone's group about 10 years ago, but now he has his own group at the Max Planck Heidelberg, and they see a lambda over delta lambda of 500, but I would have expected that it was going to be more like 2000. This is the infrared cycles, 30, and the harmonic was 69, so roughly it's a little over 2000. So why did they get a bandwidth of 500, which is wider? What was causing the broadening? Basically, I don't know. Maybe it's just instrumental width. I just don't know. But at any rate, I think that the idea of 1 over n times 1 over h is about right. Okay, yeah, this is it. The lambda over delta lambda, or its inverse, should be harmonic number times the number of IR cycles. Okay. And so then also, suppose you produce a 200 attosecond pulse, and you put that onto a multi-layer mirror. If you have a lot of bilayer pairs, 40 bilayer pairs is this. This is the reflectivity curve for a multi-layer mirror with 40 bilayer pairs, and it's not wide enough to support the full attosecond pulse. It'll trim it. This multi-layer mirror with a 200 attosecond pulse incident on it would cut it off here, and you'd lose the ends. Okay, that multi-layer will not pass that the different wavelengths associated with an attosecond pulse. So it's a short pulse. It has a broader spectrum. Okay, so it just says that, okay, I better use a multi-layer mirror with only 10 bilayer pairs. The reflectivity won't be as high, so lose a little bit, but we could get the whole, it could handle, this is its curve, it could handle the full spectrum. Okay, so that was the conclusion of this. And this was by Yanwei Liu. How else to get attosecond pulses? This would be what's shown in red is supposed to be a Ti-sapphire pulse. Okay, 750 nanometers, it says. One cycle is 2.5 femtoseconds, and you could see that this is a little bit more than 2 cycles. Okay, this is 2 cycles here, peak to peak, 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 but there's still a little bit more out there. So this is a little bit more than 2 cycles long. But if you can stabilize the envelope, so this red curve is not shifting around back and forth in here, that's what they call a phase stabilized carrier envelope, then you could wind up with the peak of the pulse always coming at a certain time, and you could trim this. You could only look at the harmonics that occur with a high enough intensity to get this little peak here. And so even though you were driving this with more than 5 femtoseconds, maybe 7 femtoseconds, you could get a really short attosecond pulse. So that's one way to get, and it's another way to get an attosecond pulse. And this is just showing this is showing 2 cases. One where you have the phase stabilized thing, just like we saw before. So you can imagine this envelope around the red curve. And this is a case where it's not been stabilized, okay? And this is a case where you could, rather than produce 1 pulse, you could produce 2 pulses of high intensity, okay? This is how you measure these things. So these pulses are very, very short. So this is a conventional street camera. This is not for high harmonics, but this is an electronic camera. But this is a good model if you want. It's easy to understand, and then you can see how they make attosecond street cameras. So in this case, the way this works is this is a tube from the cathode here, has some voltages applied, et cetera, and an output fluorescent screen. So you can imagine drawing a vacuum vessel around this thing. And it's only going to be photoelectrons on the inside. So here comes an incident light pulse. It has some time duration. It's shown to have two peaks, one big peak in the beginning, and then a little bit later, a lesser peak. As these photons arrive here, the front at the foot, they produce photoelectrons. This is a cathode. So this light hits the front, and out on the back comes a photoelectron. And there's a voltage applied here to pull those electrons off and make those electrons transit here as quickly as possible. It has to do with the resolution you can get. If these things go too slowly, you don't get you lose resolution. So the first electrons produce some photoelectrons, not so many. But as the later part of the pulse comes in the peak, you're producing a lot of electrons a little bit later than the first electrons, and then down again. And then the second pulse arrives, and the same thing happens. Not too many electrons, more electrons. And so there's an electron pulse here, which mirrors the light pulse, and it's being pulled out by a high extraction voltage. And then those electrons go, and if you didn't have anything else here, those electrons would all just pile up in the middle of this fluorescent screen, and you just have a bright dot. But what happens is, as they're coming through, there's an area here where there's a transverse electric field, a high voltage, and it's a ramp up in time. And the ramp, I didn't show the ramp here, but it starts with a low voltage and it ramps up. So with low voltage or no voltage, the earliest electrons go over here. Oh, I'm sorry, the way it's set, they would go over to the left, okay? But this ramp and voltage pulls later electrons to the side. So I guess the electric field is going this way, the electrons go the other way. And so the time structure of the electrons here, which is one-dimensional in this axis, this transverse electric field spreads them out transversely. So this ramp voltage, okay? And this hits a fluorescent screen and light comes out, visible light comes out the backside, and it reproduces the incident light pulse. So this is called a streak camera. This is called streaking, okay? And it's a conventional method that's decades old, many decades old. And yeah, and it's widely used. So then comes the Attosecond streak camera, or streak recorder as they want, okay? And so let's see if I can explain this thing. There is, what I don't see here, there's the infrared pulse is coming along and it's propagating this way. And the X-ray pulse is also coming along, okay? And you put some atoms in its way. Let's just say a small volume of gas. So the atoms are here. And you can, by the way, it's important that you be able to change the relative phase of this X-ray pulse or EUV pulse with regard to the peak of the laser pulse. So here's our laser pulse. Here is our EUV pulse that we'd like to know what is its duration, or what is its time structure. So notice that this in the violet here looks like this in the blue here. So this was blue something coming in, light pulse. And this is the one that we want to measure. So as it comes through, it has a high photon energy. It can knock electrons, pull electrons off these atoms that are here. And this can be intense enough. And it's the right photon energy to just pluck out electrons. So it plucks out electrons, and then there's an applied field that pulls those electrons towards a detector, okay? And so by changing where I'm sorry, I said there's an applied field. The streak, the transverse electric field that's doing the streaking is now the infrared pulse itself. It has a rising, it's going from 0 voltage to a higher voltage. So you don't want to operate at the peak. You want to operate on the slope here so that you get a gradient in time that matches this ramp in time. This is now your ramp voltage that's sending on half a cycle electrons towards a detector, and you record them, okay? And so this is the streak, this is the Attosecond streak camera. And so the incident X-ray pulse or EUV pulse is producing electrons, and then the sloped part of the infrared pulse is acting as the transverse field, accelerating the electrons. And so that's the analogy, and they call it an Attosecond streak camera. And this is some sort of data. Yeah, so here's some data. This is a recorded data, and this is their analysis then in time and in frequency space. So here's some of the factors. The Thai sapphire was at 720. It had a 3.3 femtosecond full width at half max. It produced 80 EV photons, a half a nanojoule of them, and the conversion efficiency was 10 to the minus 6. And it was published in this paper in Science. And so this is their analysis of this streak record. And it was published as 80 attoseconds, plus or minus, and a 28 EV bandwidth. And you notice this is not, it's a little ratty, it's not Gaussian. So this is not quite what you'd call a diffraction limited pulse, okay? The full width half max and the in time and in spectrum, if you multiply these two numbers, you're not going to get the bandwidth limit. It's off a little bit, and it's because of all this structure, and it's a little too wide, but it is what it is. So this was the first result where there was really good data on a sub-femtosecond pulse, and this was in 2008. And I was going to attach the papers because Andy Aquilar, who's now at SLAC working on the FEL, this was part of his PhD thesis. He made the multi-layer mirrors for this, and they had concentrically, let me just see if the next slide shows it. No. Concentrically, an EUV mirror inside of an infrared mirror, and one could move compared to the other. So that's how they managed to get the time shifting here. Both the EUV and the infrared came out of the gas. The high harmonics came out of the gas, and there was a filter there to choose certain photon energies, but they both hit sort of the same mirror, but it was an outer ring mirror for the infrared and an inner mirror for the narrower cone of the high harmonics. And they could shift, actually just move one compared to the other, and these two would shift. The purple and the red would shift compared to each other. So that was part of Andy's PhD thesis. And the second paper involved the same lead author. These are all in the Franz group at Max Planck Garking. But the second paper with equal co-authors, Goulimakis and Zhihang Lo, who was in Steve Leone's group. Okay, and that was, what was that? 210 versus 208. So those two local PhD students contributed here with their own PhD theses, and both took this class, by the way. So okay, so this is just some more of the Attosecond, what Steve and his group have called, Attosecond streak absorption spectroscopy. And now everybody uses that phrase. And basically you produce attosecond pulses, which have a very broad spectrum, and put it through some molecular gas or something that you pump to, and you look to see how does the absorption spectrum change as a function of time. So there's attosecond science among the first papers. Okay, and then I think here, this is just another example of doing the same thing on a solid state tungsten. And by the way, these things matter to you because in the homework assignment, which I guess Stefan will issue either today or Friday, one of the questions involved, a few of the questions were, how does this whole thing work? You know, what's the three-step model, et cetera, et cetera. But the last question is, what was some of the science that's been achieved with attosecond pulses? So this is one. This is another where they're looking at crystals, at emission times in crystals between valence band and core levels. What's the difference in emission time? Okay. And by the way, so here you can see there's a little bit more. Oh, here's the delayable mirror, the delayable EUV mirror with an annular IR mirror that I was just talking about a moment ago. So that's for the streaking. So what limits IR harmonic conversion, the return efficiency is a big one. The IR path, the 800 nanometers path, the 800 nanometers is affected by the electron density. So if the electron density gets too high, the 800 nanometers or the IR is affected by that and is strongly refracted out of the gas. Okay. And that's something you have to worry about. So there's both possible absorption, and there's also this losing the intensity of the infrared pulse because it's diverging out, and also because let me see if there's perfect. So here's our scheme, right? There was a laser focusing light to for example, a gas jet. There are variants on this, and the infrared continues out, slightly diminished, but the harmonics come, all the harmonics come, and you can put a filter here that will block the IR, usually an aluminum filter, for instance, and then just the harmonics come through, okay? But here's an enlargement of this whole thing, and this is showing the infrared driving pulse, the laser pulse coming in a few femtoseconds into the gas, and there's an interaction region defined by where there's gas and where there's infrared light. So this would be the interaction region, okay? And in that region, you produce UV photon, XUV or EUV photons, and that come out. But for instance, what happens is the EUV produced here could possibly get out of phase with the EUV produced here. And that would be what happens with the EUV photons have a certain phase velocity, okay? But the infrared light in this gas also has a certain phase velocity. It's not so much affected by the atoms, but if the free electrons are there, the infrared light pulse will, one, diverge a little bit more. There's a sort of negative lensing effect, but more than that, the infrared light could get speeded up. It'll go higher phase velocity than the EUV. And if it gets, for instance, if it develops, you know, they start here where they both have a certain phase relationship, but if it goes along here and there's a pi phase shift between the two, okay, then the photons here are going to be out of phase with the photons that were produced earlier, and they're going to cancel. And so if you make this path too long, you will get less EUV photons. You'll start seeing less. So if you played with that as a function of length, okay. And so this is a plasma effect. And I have a few slides at the end, which if we don't get to today, we'll get to at the beginning of the next class. And how are we doing? Oh, we're over at time. So I guess, so anyway, that's an important thing. You can have a dephasing and you can lose because of dephasing. And so this graph showed that in low harmonics, absorption was the main problem of limiting how thick you could make the sample. For instance, you could imagine, you'd like to make this as long as possible. This is an n-squared coherent effect. And if you made it longer, you'd have more atoms and more photons, and you'd get an n-squared effect. But there are these two factors which limit it. One is absorption, and one is dephasing, where the infrared starts to run too fast for the harmonic. And there's a few slides here, which I'll go over very briefly at the beginning of next lecture. And also, Bailey is going to show a 10-minute video of the high harmonic lab that she works in with Professor Zurch. And so she'll show that, and I'll go over these last few slides, but basically I'm just going to tell you that there are examples, and you can read in the book, where absorption plays a role and where phase shifting plays a role. And it goes through, and there's a lot of detail here about the different phase velocities. For instance, how is the infrared affected by the atoms and ions, and how is it affected by the plasma? And what about the EUV? How is it affected by the atoms and the ions and the electrons? And you go through this. And so there's a lot of tedium here, and maybe I just won't go through it. I'll just tell you now. You can read about it, but there are different ways of estimating when there's a pi phase shift. So some people call this a coherence effect. That's not correct. I mean, there is coherence is playing a role here, but what's happening is it's a phase shift between the driver and the harmonics that are produced. So I call it a dephasing distance, not a coherence distance, which many people do call it. Okay, so here's the stuff. I think for the high harmonic people, it's very interesting for you to have a single slide or a few slides where you can confidently say, what is this refractive index in the plasma that's leading to this dephasing? And so I'll save that for the next class. it works well because it's a plasma effect, and we're going to start plasmas in the next lecture. So I think that's pretty much where we'll end for today. So thank you for your good patience. And any more, so I think we had a little discussion on the projects of duration and stuff. I'll wait to see who sends me more emails over the weekend, and we'll address it again. And one person has volunteered, I think, to go kind of early, and that would be good. And there's also the suggestion that we do it, and not in 4 sessions, but by having a little bit less time. For instance, the 12 minutes plus a few minutes for discussion or something like that, and do more people per session. So that way we could, the last 2 scheduled classes we could use, and then either another class set, another session set for the presentations, either in the R³ week, which is probably preferable, right? Because you're all graduate students, so you're not affected as much, you know, you're not in as much need for the R³, I think. So if that's okay, again, feedback would be most welcome, and the more people that respond, the better. And we can set some timing, like goal of 12 minutes and 6 or 7 slides. But if somebody needs a little bit different than that, or some group of people finds something, and again, the emphasis is not on this being a mini conference, but rather an educational, a chance for you to practice teaching and for the class to learn some concepts here. They may not swallow everything you tell them, each other, but okay. So I think we're ready to break, right? Is that okay? We are ready to break? Okay. See you all on Thursday.